select set of topics, mostly biased by my experience. But I'll try to give you some introduction to a wide variety of tools that people are applying these days. And I noticed that in the chat that many of you have physics background, which is great. I will try not to spend too much time on jargon, but I will begin with a little bit of introduction to motivate why we're talking about this subject. So first, I should say a little bit about fundamental physics. So right now, we're kind of interesting crossroads for the largest scales in the universe and the smallest scales in the universe to understand the fundamental properties of nature. And they're interesting theoretical and experimental questions that motivated deep exploration. And I'm not going to spend too much time talking about this, but I'll just say a few things. On the left, there's a picture that sort of motivates the search for dark matter, for instance, where you can see this is a picture of two colliding clusters of galaxies, where there's the gravitational matter is in purple and the visible matter is in pink, and basically the centers don't align. So there's some additional gravitational matter out there in the universe that's not explained by the visible matter that we know about. And another interesting question, which is shown on the right, is a deep question about neutrons, which are a fundamental property that are part of all the atoms that we know about. Most of the pictures online look like the picture on the left. They're made of quarks. There's two down quarks and an up quark, and they're usually arranged in a triangular fashion. But actually, in nature, they're like very linear in a line, and we don't totally understand why. And there are a variety of other questions that motivate a deep exploration. And in order to answer these questions, we've performed thousands of hypothesis tests, and so far have found no significant evidence for physics beyond the standard model of particle physics, which is the tool we have that explains all the things we know about so far. But it has some key gaps, which are sort of some of these buzzwords that are highlighted in the light colors above. And so this really has motivated us that we need new tools to explore our data in new ways. And so that's what I'm going to tell you a little bit about today, and how machine learning could provide a solution to that. So the first thing we need to do, of course, is build detectors that are sensitive to new physics. And so here are just a small set of detectors that represent various aspects of fundamental physics experiments. Of course, there are many others. So there are experiments that are directly probing dark matter in astrophysical sources, or creating synthetic particle sources in a lab. For instance, there's neutrino experiments that are beaming neutrinos from Chicago to South Dakota. There's looking for dark matter directly interacting with us on Earth. There's a Large Hadron Collider in Geneva, Switzerland, where we're colliding protons together at very high energy, and other experiments as well. And maybe I'm going to focus a lot on collider physics for the rest of this talk, because that's my background, but a lot of the challenges and tools are similar and span different areas. So I thought I'd start by giving you a sense of the big data problem that we have. So here's the Large Hadron Collider. It's a proton-proton collider in Geneva, Switzerland. And the collision rate is 40 megahertz, and each collision is about a megabyte. So we have this detector. It's huge. It's hard to see in the bottom left of my screen here, but there's a tiny little person here for scale. It's the size of a 5-story building that's 100 meters below ground, and there's something like 100 million readout channels. So with a megabyte per collision at 40 megahertz, we produce data at a rate of a zettabyte per year, which is an incredible amount of data. Now, we can't possibly write all this to tape or to disk, and so this is really the edge computing requirement. And we throw away almost all of our data in real time, 99.98% of it. And the final data set that we actually physically write to memory is in the exabyte range by the time the data set is done. So this is a serious data set. It's not the biggest data set that's ever been collected or will be collected, but it's possibly the largest scientific data set, and it's not tiny compared to some industrial data sets. Okay, yeah, maybe I thought I would just for humanity show a brief aside on sociology. So in order to collect this data set, it's an enormous amount of work by many people. Here's a small fraction of my collaborators in the experiment I work on in Geneva, Switzerland. We were celebrating the Nobel Prize-winning discovery of the Higgs boson some years ago. And you can imagine, yeah, I'm a little person here in this entire scene of many people. And in fact, all of our academic papers have all thousands of authors on it. So this is the author list of one of our papers. There's a person whose last name starts with AAD. It's alphabetically ordered. And if you scroll down through the author list, you eventually find me somewhere in the middle. And so it's really team science to the fullest extent. Okay. All right, so yeah, back to the detectors. To complement the detectors, we also need methodologies. So we rely heavily on simulations, advanced technologies on the accelerator side to create synthetic memes, for instance, on supercomputers to do the heavy compute, and then for a variety of other tools as well. And the combination of the advanced detectors with the advanced methodologies is a huge challenge, but also a key opportunity. And our detectors, they're these multi-layer, highly redundant detectors that I like to think of as like hyperspectral cameras. And if I think about it that way, then for instance, here's a schematic picture of what a collision might look like at the Large Hadron Collider, where we have two protons, like these sandwiches there, are these balls of quarks and gluons are being slammed together, and out goes a spray of particles. And given collision at the Large Hadron Collider might produce 1,000 particles. Each particle has information like its momentum, where it's going in space and its energy, and other properties as well, like its electric charge. And so that easily spans 1,000-dimensional space. And then we're going to measure that with these colored lines here represent detector elements. And we have a variety of detector elements that redundantly measure various particles so we can get precise determination of their energy and trajectories. And there could be like 100 million readout channels. And so this combination of a large phase space we're trying to measure with a large detection space is a huge challenge. And deep learning really is an opportunity to help ameliorate this challenge. So we have what I like to call hypervariant vision with deep learning. We've been doing multivariate analysis for years, but it's possible that one of the reasons we haven't identified something new is because we're not looking at our data holistically in its natural high dimensionality. And so deep learning might be able to allow us to see patterns in high dimensions that we would not have been able to see otherwise. And so I want to tell you a bit about that in the next slides. Okay, so roughly speaking, data analysis in particle physics has the following structure. So we ultimately want to do inference about nature. And so we have sort of two parallel streams. There's the experimental stream on the right and the theoretical stream on the left. So obviously there's nature. We build experiments to observe nature. And then we identify some observables that we can use to do some dimensionality reduction and then infer something to be able to do our downstream analysis. And we have a parallel stream where we have our theory. For instance, the standard model of particle physics has some parameters. The current standard model has 20 some parameters, but there are extensions of that model that have, can have up to hundreds or more parameters. Then we can take those theories and simulate them so that it's produce synthetic collisions that look just like the real ones that we would have in our detector. And then we can run the same downstream tasks in order to basically make a direct comparison between data and simulation. And sort of a unique feature of a lot of fundamental physics experiments is that this left pipeline is very precise and accurate. So we can produce for a given model, we can produce synthetic data that looks almost just like real data and can be used for inference. And additionally, it comes labeled because we simulate it, so we know exactly what we're doing. And deep learning is playing a growing role in basically all steps of this chain, both on the theoretical side and the experimental side. And then my goal today is just to highlight a few key places where deep learning is making a big impact. And I'll just say a few things here. So in particular on the experimental side, we're using machine learning at sort of at the edge for online processing and data control for a variety of other fast inference tasks. And then offline for various forms of data curation, like calibrating our detectors, doing pattern recognition, noise mitigation, et cetera. On the theory side, we're using generative models for speeding up simulations. I'll say a bit more about that, as well as for the inference problem, which I'll also talk about in a little bit more detail. Okay. Oops. Great. So now I just want to walk through basically a series of examples. And let me start over here with this detector level observables and going and doing pattern recognition. This is the place where most of the machine learning has been applied so far, basically using machine learning classifiers to enhance our sensitivity to various kinds of new physics. And then I'll talk about some of the other areas that we've been exploring broadly for the last years. So this arrow here to do pattern recognition has many steps, starting from the lowest level, sort of at the readout of individual detector elements to noise mitigation, pattern recognition, but then also for calibration, and then downstream, very close to final analysis, where we want to develop observables using machine learning that can be used directly in the statistical analysis. And so this spans quite a huge range in the experimental process. So let me give you just a couple of examples. First, I'll give you an example from noise mitigation. And the example is in the context of what we call pileup. So for instance, the Large Hadron Collider, this is what an example event might look like. In this picture here, the protons are coming from the top left and bottom right, interacting in the middle, and out goes this huge spray of particles. This is one collision event, and each purple line here corresponds to an outgoing particle. And we don't actually collide single two protons at a time. That would be an incredible waste, because most protons actually don't collide at all. We collide many protons, and in fact, the average number of collisions is not one; it's much more than one. And the extra collisions that we get, so you usually have one collision that you care about, and then a bunch of other ones you don't care about. Those other ones are called pileup, and they basically add noise, so noise particles on top of our event that we don't care about. In this picture on the bottom left, you can see along the beam line. So this line here is the beam axis, and then what I'm showing are the reconstructed proton-proton collision vertices. You can see this is this light colored one, the teal one, is the collision vertex we care about, and there are many other collision vertices that we don't care about, and many of them can be resolved from the one we care about, and so for those ones we can simply know that they're noise. But this is an image noising problem, but it's a bit different than image noising, because the twist is that for electrically charged particles, we can reconstruct their trajectories very precisely and measure their vertices and then basically remove them. But for neutral particles, we can't measure their trajectories. We only get a measure on aggregate the energy collected in a given point in space, and so we can't use that information to simply remove them. However, we can apply sort of modified image denoising strategies. So for instance, I can think of this image noising strategy as sort of I have RGB kind of image input. So imagine I project my detector onto a surface of a cylinder. So you can imagine like a grayscale image where the pixel intensity corresponds to the energy deposited in the location of the detector. And then it's a case where I have for the charged particles, electrically charged particles, I know the ones I care about and the ones I don't care about, the pileup and called the leading vertex sometimes. And then for the neutral particles, I only know the total. And so I can use these three channels to predict the neutral particle content from the vertex that I care about, for instance, using CNNs. Okay, so that was one example, first example of using machine learning for noise mitigation. Now let me give you another example at sort of the very end of the analysis stack, where we want to develop some classification tasks, for instance, for particular analysis. So here's another picture of a proton-proton collision. The protons come from the left and right, and the orange lines and green and yellow blobs correspond to charged particles and energy deposited in our calorimeters, respectively. And we can reconstruct all these particles in order to infer something about what happened at the center of the collision. And in particular, one of the goals of the Large Hadron Collider is to identify new massive particles. And so we want to pump in a lot of energy. And if you remember, E equals mc squared, and that says that we can trade energy for mass. So if a new massive particle, we can pump in a lot of energy to make the new massive particles. And we want to be able to do this inference with all the available information. So all this yellow green blobs and orange lines are information we want to use holistically in order to do this inference. And so, as I mentioned before, we can sort of project onto images, which is one strategy, where you can imagine I take the event and I project it on the surface of a cylinder, and then the event looks not unlike an image. And we can apply CNNs. So for instance, we can think of the whole event holistically as an image, where there can be multiple channels corresponding to different detector elements. So you can imagine like the charged particles and the information from the calorimeters. And we can also have regions of interest. So we can focus in on regions of the detector where we know there might be something of interest. And we can have, for instance, a more precise, finer granularity. And then we can combine these two streams in order to do a classification task, like, is this something new or is this something standard? And there are some variations that we have to think about. So for instance, like this is a cylinder. So cylinders, of course, have a 2 pi symmetry. And so when we do like a CNN on the full event, we need to be careful that we do some padding or apply other techniques in order to respect that symmetry. But if we do that, we can achieve significant improvement in the state of the art. So here's a plot that shows the signal to noise ratio for the identification of a very important channel, the identification of high energy Higgs bosons. And this is the amount of data on the x-axis, and the y-axis is the SNR. And without machine learning, with this gray dashed line, and with a machine learning technique like the one I just mentioned using CNNs, you can improve the significance by quite a bit, which basically corresponds to having a discovery earlier or having a more significant discovery for the same amount of data. Okay, so yeah, now back to my my picture of the analysis pipeline. I just told you about the detector observables, the pattern recognition component. Now let me tell you about some other areas. And in particular, I want to focus on this, this path here. So going from a theory of everything to physics simulators. And there's a growing toolkit of generative models that are being developed to accelerate our simulations. So our simulations are excellent. They're very precise and based on first principles physics, as well as combined with some phenomenological models, but they're often very slow because they try to incorporate all the details. And so you might imagine that we can take the best of our physics simulators and the best of machine learning to make a new hybrid. So training neural networks can be slow, but the evaluation is incredibly fast. Whereas physics-based simulations are very slow. So the question is, can we pay a big upfront cost or a relatively small upfront cost to train some neural networks to mimic a physics-based simulator and then later sample from them in a much faster way than the original physics-based simulator. And so here's, for instance, a picture of an example I'm going to show, which is one of many that are ongoing, where we want to simulate the energy deposited in a calorimeter. So say you have 3 layers of a calorimeter, which is nothing other than you have chunks of material, and we want to know how much energy was deposited in those materials. And here it has 3 layers, and the granularity is not the same for each layer. So it's a bit different than an RGB image where each pixel is the same size, the different size pixels, and there's a sort of causal structure because the particle had to go here before it went here, before it went here. So we're shooting a particle, say this way, and it deposits energy in each layer. And there are a variety of tools that we can use, but as probably many of you know, the basic principle of a generator is nothing other than a map, a function that goes from random numbers to some structure. And in this case, we want to produce the structure, the image of the energy deposited on each of these layers. And one tool that can be used for this, although there are others, is the generative adversarial network, where we have trained 2 neural networks, one that maps noise to structure, that's the generator, and another one that determines if the images that are produced came from the generator or from our physics-based simulator. And then when the discriminator, they're trained at the same time, and when the discriminator is maximally fooled, then the generator is doing a good job at reproducing the physics-based simulator. And this seems to work pretty well. So here, just an example in this particular case I told you about, the top row shows the average images from a physics-based simulator, and the bottom row are the images produced from a GAN trained on the physics-based simulator. And this is now from a few years ago, but the state of the art is achieving high precision, not just on average, but also using in the full high dimensional space, which spans 1,000 dimensions or so. And the main reason we want to do this, of course, is the speed. So the physics-based simulator, which is in this case is called GEANT, is quite slow for very precise simulations. But if you, for instance, use a GPU, and this is not even the latest and greatest, and you use batching, then you can achieve, say 4 or 5 orders of magnitude faster. Now these numbers are both the traditional and the machine learning based approach to both getting better, but this I think illustrates the potential of this technology to qualitatively improve what we can do with our simulators. Okay, so now moving on to another topic is the inference problem. So going from using our simulators to go from the observables that we see back to some properties of our theory of everything. Now, our physics-based simulators are great. They're a unique and powerful aspect of particle physics, and I would say fundamental physics more generally, but they often do not allow us to go backwards. So they allow us to go from the theory to the data, but not from the data directly to the theory. And so we need other tools in order to do the inverse problem. And so in particular, let's say one way of sort of summarizing this in pictures is that we measure some detector signals, the charged particle trajectories, these energies deposited in our calorimeters, and we want to infer something about what the particles before the detector would have looked like that would have made those patterns. And then we can also, so we can infer the particle properties and then also properties about the underlying theory. So the model parameters, for instance, the masses of particles, the strength of their couplings, et cetera. Okay, so if we knew the probability of the measured spectra given the true, we could for instance just say, okay, let's just you could unfold the detector effects by doing maximum likelihood. Probability of the measured given true, we just maximize the true. And the challenge, as I had mentioned at the beginning of my talk, is that the measured is this hyperspectral data, and the true is some high-dimensional feature space. And so this probability density is intractable. We basically almost never know. We almost can never write down P of measured given true analytically. However, we have simulators that we can use to sample from P of measured given true. And often these simulators are not differentiable, but they still are, allow us to sample. And this has led to a lot of interesting innovations in what some people call simulation-based, or also maybe a bit broader term is likelihood-free inference. I think this is an area where machine learning, where particle physics is making an important contribution. So let me just give you one example of likelihood-free inference, and there are others. So one tool that can be used in this area is to exploit the fact that neural networks learn to approximate likelihood ratios. So if you want to do inference, often you need to know, p of x. Let's say you want to do max likelihood, you need p of x given parameters or given the true. And it may be impossible to know that, but it may be easier to compute ratios. And so neural networks directly compute likelihood ratios. And so that might be a solution that turns the problem of density estimation, which is a hard problem, into a problem of classification, which is much easier. And this is really very important for particle physics in particular, because our collision events, they or other kinds of data that we produce, they have a variable number of particles, for instance. They're not like a fixed length, which have a lot of symmetry. So all the particles, thanks to quantum mechanics, are interchangeable. There's no well-defined order. There are other kinds of symmetries that are induced, for instance, like energy conservation, momentum conservation. And these are relatively hard to bake into a generative model, especially in high dimensions, but a classification model can readily incorporate them. So here's just a picture, to illustrate, let's say you're colliding two electrons and outgoes some particles, and they have a really complicated structure. Okay, and I'll just give you one very brief example of how this can work. So imagine I want to take some sample that I have from a generator, and I want to morph it into another one. This is a very common problem in the first step in an inverse problem inference chain. So let's say I have some collision events like I was talking about. So two electrons collide, they produce many particles, and I have, I can't visualize that space. It's high dimensional and also variable dimensional, but we can compute one-dimensional observables and make histograms. So here are some histograms of these kind of events where we have, for instance, just count the number of particles. It's a very simple observable. And you can see it's not the same number of particles for every event, so that's random. And we also have some other more complex observables, like this is some 3-point correlation function. It doesn't matter so much what it is, but it takes into account the energies as well as the positions of the various particles in the event. And the point is that we can, for instance, train a classifier between the blue and the black, and then we can use this technology to interpret the neural network outputs as likelihood ratio estimators, and then we can morph the blue into the orange, which matches very precisely the black. Basically everywhere in the phase space, and even not just in these two dimensions, but everyone you can possibly imagine. And this allows for a really very powerful strategy for doing inference. Okay, so then the last topic I want to highlight in my talk today is anomaly detection, which I've drawn here with these arrows to try to highlight different strategies that can be used for looking for new particles. And this is something I'm particularly excited about recently, in particular because we have no evidence right now, significant evidence for new particles, but that could be because we're sort of tethered to our models, and maybe there are more model agnostic ways to allow us to look for things that we didn't know how to look for otherwise. So yeah, now let me give you just a little bit of a taste for how searches for new particles work. So trying to look for the famous question mark particle and how they can be augmented with machine learning. So the way a traditional search would work is that we posit some model. So supersymmetry is a very popular model, or a class of models rather. And we take some supersymmetric model, and then we can, given the parameters, we can simulate it, and we can make synthetic events that look just like real events as if they would have come from supersymmetry. Then we do some very significant dimensionality reduction, where we use our physics intuition to form very simple observables that are basically combinations of momenta of particles that we know should be relatively sensitive to the parameters of this model. And so we can basically summarize the strategy as using well-motivated but theory-biased and low-dimensional observables to do inference. Now, the question is, can we augment or complement this strategy with more model-agnostic approaches that relax the model assumptions on what the new physics would be, as well as explore high-dimensional feature spaces holistically instead of having to impose some physics structure on what the observables should be ahead of time. And so, yeah, what if we're not looking in the right place for the new stuff? Now, there are a variety of challenges that we have in doing these kind of searches. One challenge is that learning from data without having some simulations is really challenging, in particular because it's basically impossible to produce labeled data. Even if you paid trained physicists to label data, it wouldn't be possible. And that's because our kind of learning problems tend to be a bit different than, say, learning cats versus dogs. Like here, you can look at these pictures, know the left one is a cat, the right one is a dog. But thanks to quantum mechanics, a lot of our events, it's not possible to know on an event-by-event basis what produced it, because anything that could have happened will happen, and it's only on a statistical basis that you can say anything significant. And so the usual case is where you have, like, let's say in simulation, you can produce events of one type and events of another type, and then make labels and label one as signal, one as background, and then train a classifier. But in data, the problem is more like this, although this is a very extreme case where you might have mixed samples, and then you might have some superposition of signal and background, and you might have two mixed samples that have say different amounts of signal and background, where you can observe everything about these balls except their color and their label. And in that case, the question is, can we still learn? And there are a variety of tools to learn in this case that are less than supervised, so unsupervised, weakly supervised, semi-supervised. And one example, which I'll just highlight here, goes by the name classification without labels. And the idea is that very simply, if you can construct these mixed samples, you can simply assign labels. So everything in this mixed sample is, say, 0 and this as 1, train your favorite classifier to distinguish them. And then you can show that classifier is asymptotically optimal for distinguishing red from green. And this is, has basically a one-to-one correspondence with label noise, where you can think of these labels that we're assigning as noisy labels, and then all the technology from noisy label learning basically carries over here. So now I want to just briefly show you in the last minutes that I have to talk about how we can use this classification without labels, or koala paradigm, for looking for new particles. And yeah, this to be clear, this is the koala is like the koala bear, and this one here is being freed, not captured. So it's koalas that are hunting and not hunting for koalas. Okay. All right, so let me show you how we can use this approach. In many searches for new particles at the Large Hadron Collider and elsewhere, there's typically a known dimension where the known physics is sort of smooth, and the new physics, if it exists, would be resonant. So if you're looking for like a particle with a particular mass, then it will be then you can construct a dimension where it will be resonant because it will be resonant at the mass of that particle. And so we need, in order to set up this approach, although there are others that don't have this requirement, we need to have one dimension where the signal, if it exists, is localized. Now, we don't have to know where it's localized, because we're going to eventually scan over this. But then once we have that, we can construct two mixed samples. We can, for instance, construct a signal region and a sideband region, where the signal region would be mostly background, but then maybe a little bit of signal if it exists, whereas the sideband regions would be basically all background, maybe with a tiny bit of signal. But the point is that the signal region would have more signal if it exists in the background. And then we can use whatever other features we like in order to train one of these koala classifiers, where we can basically train a classifier to distinguish the signal region from the sideband region. And if there is a signal, so some subpopulation that's statistically different from the background, then the classifier would automatically detect that without us having to tell the classifier what the signal was to begin with. So I want to just briefly highlight how this would work in practice. So here's a picture of a collision event at the Large Hadron Collider, where the protons come into and out of the page, and you have this spray of particle transverse. And in this case, there are this red labeled spray and this green labeled spray. These two sprays are called jets, which are clusters of particles that are sort of going in the same direction. And they correspond to the decay of quarks and gluons or other particles. And these yellow blobs correspond to the energy deposited inside these jets. And so one can construct a search of this kind by looking for the invariant mass of these two jets would be the resonant feature, because if there was a heavy particle, the famous question mark 1 particle, it would decay into stuff whose invariant mass would reconstruct to the mass of that particle. And then you can use all the other properties of the jets to see if there's any other evidence for some strange structure that could help enhance the presence of this kind of topology over the generic background. So let me walk you through how this would work. So here's a picture that shows a histogram where it's the number of events in bins of the mass, the reconstructed mass. And we construct a signal region and sideband regions. These blue points correspond to the stimulated counts in each bin. And then importantly, we need to estimate, we want to compute p-values. And so we can do a parametric fit where we exclude these 3 points here and then fit with all the other points. Then we can interpolate into the signal region and compare the red interpolation with the blue points to compute a p-value. And then we can repeat this procedure for different threshold cuts on this koala classifier. So we train a koala classifier, and then we can keep, for instance, the 10% most signal region-like events or the 1% most signal region-like events, and then repeat the procedure to compute p-values for all the different threshold cuts, 4 of which are shown here. And then we can compute p-values, and this right plot will be our ledger of p-values. So for the signal region that's shown here, all the p-values are sort of order 1. They're consistent with nothing interesting. And then we can scan the signal region from left to right. And as we go from left to right, we can continue to compute p-values. Basically, as I scan, and I'll just do it again, the top line doesn't change, but the other lines change. And that's because the classifier depends on the data. And so the classifier will be different in every region because there'll be different statistical fluctuations in each region, which will correspond to different classifiers. But overall, the story is that when there's no signal here, this is the simulated background only case, we have p-values that are all order 1. So that's good. It's important if anomaly detection procedure, if there's nothing new, it doesn't find anything. That's obviously necessary, but not sufficient. We also have to be able to find new things. And so now let's inject a signal. So here's some new physics. Doesn't matter what it is. Some heavy new particle that decays into some other particles that decay into sprays of other standard model particles, like protons and electrons and muons and other friends of theirs. And the orange histogram here corresponds to the signal that's lurking underneath this huge background. So you can see it's many orders of magnitude below the background. And so without any machine learning, we wouldn't be able to find it. And we can run the same procedures. We can scan the signal region from left to right. And as we do, the p-values start boring when the signal region doesn't contain the signal in it. And then once the signal region overlaps with the peak of the signal, you see the p-values plummet. So the neural networks have automatically identified some subpopulation, which is statistically different between the signal and between the sideband region and the signal region. And you can just see the bump here by eye. So basically, when we make a threshold cut of the most signal region-like events, it's very efficient on the signal and very inefficient on the background. And so it preferentially keeps signal, preferentially throws out the background, and you get this nice bump that forms. And that corresponds to p-values that are very low and a very high significance for discovery. Once the signal region then passes over again, the p-values return to their order 1 numbers. And you can see we basically took this, this excess, which started off as a 1.5 excess, 1.5 sigma excess, and turned that into a 7 sigma discovery. Okay, so this is just a summary of that here, where if we didn't inject anything, we get p-values that are order 1. And if we inject the signal, we can take p-values that go from order 1 down to something like 7 sigma. All right. So that is going to bring me now to the end, start wrapping up. Today, I've told you about various aspects of machine learning that are playing a growing role in the experimental pipeline as well as the theoretical pipeline. I used collider physics as my example, but this is being applied throughout fundamental physics. And there are a variety of common themes that are being used for online, offline data processing, as well as for the various inference tasks. And so now my last slide, I think deep learning has a great potential to enhance, accelerate, and power discoveries in particle physics. I think we have some unique challenges that require dedicated solutions, but I also think that there are some tools that we can borrow from industry, as well as possibly some solutions that we can provide that might improve machine learning elsewhere. With these tools, we'll be able to fully exploit the data and their natural high dimensionality, enhancing the potential for discovery, I hope. And the last thing I'll say is that if you'd like to learn more, I'm one of the organizers of this online review we call the Living Review for Machine Learning and Particle Physics, which is a basically updated every week, where we add new papers that are by category, including reviews and other subtopics where you can read about the latest and greatest in machine learning for particle physics. And that's it. Thank you.
All right, great. Thanks for the presentation. And I think we have some questions in the chat. You can open up the chat to go through them. Or, if you want, I can read the question to you.
Yeah, I see that many of them came through as I was going, and I wanted to make sure I got to the end. So maybe I'll let you decide how best to go through them.
Yeah, I think we can just go from, I'm opening up the chat. We can just go through from the top ones.
Okay, yeah, I'll do that then. So yeah, I think I see Alex Colo asked the first one. So yeah, you say no evidence about dark matter and energy. So yeah, so that's a very good question. So we definitely know dark matter and dark energy are out there, but we have no idea what they're made out of. And so by no evidence, I mean we don't know what the dark matter. We know that it exists. We don't know anything about what it's made out of, what its composition is. Should I just keep going through the questions? Bill?
So the next one is how much information is lost?
Oh, yeah. Yeah, I'll just keep going then. Yeah, so the next question, yeah, how much information is lost? That was about, I'll just go back up to that. Talking about the online, the trigger. So a lot of basically, if an event is not saved, I think I had it here. Yeah, if an event is not saved, it's thrown away forever. So for every event we save the whole event. And if an event is not saved, it's lost forever. And so that's a lot of information lost. Now, we design our online detection algorithms, which also use machine learning, to be basically as good as possible at finding things we think are interesting. But of course, that's biased by what we think is interesting. And so it's very possible that there are things that are actually quite important that we're throwing away. And so looking forward to future data runs of the LHC and other experiments, we're trying to move more and more of our processing online in order to make sure that we're more inclusive. Okay, the next question. Yeah, so there's a partial answer, I think, which was that, yeah, these can be considered background noise. So yeah, I mean, it's the usual problem of, one man's junk can be another man's treasure. And I think that, the selection criteria are very, are tuned to be as useful as possible, but of course there could be things that are lost. Okay, let me keep going. There's a question about if contrastive learning would work here. I don't know the physics, but I imagine there are symmetries to exploit for contrastive labeling. I'm not exactly sure what context that was discussed in, where it came in the talk. But I think that, yeah, it's quite possible that that contrastive learning and other related tools could certainly be useful. Generally. And yeah, if you have a follow-up question, you can post in the end and I will try to answer it. The next question is about machine learning and deep learning are known as black box. How do you as physicists are comfortable with that? That's an excellent question. And I would say there's been some resistance to using machine learning and deep learning in particular, in part because of that. But I think that my general perspective, and I think what's growing in across everyone, is that if we make our machine learning algorithms designed in a way that incorporates the physics knowledge and are built in a way that the result will tell us something useful, then I think that they can be trustworthy. And this is especially important in the area of quantifying uncertainties and what it means for to be uncertain about the application of a machine learning algorithm for inference. And there's still something we're trying to understand in more detail, but this is I think a really important question that we're trying to tackle as well. I think it's one of the reasons that it's taking a long time for these tools to reach the mainstream. All right, there's a question about what type of storage system and database system are used to store these exabyte of data. That's a really good question as well. I don't want to spend too much time talking about the storage requirements. That's a totally different talk. But we have a pretty sophisticated worldwide distributed grid computing setup that's used for the storage and access of all the data and metadata, and that really is essential in order to do these like large scale data analyses. a question: is there any research in antimatter relevant to data science that we are aware of, that you are aware of, to storing the stimulus energy present in the antimatter? I don't think so. Well, there's a lot of research on antimatter in general, but yeah, maybe if you have a more specific question, I'm very happy to answer it. The last question I see is, what types of language are you using to run ML models and frameworks? I would say a variety of tools. So of course, for deep learning, many people are using PyTorch and TensorFlow. Many people still use, or many people of course use scikit-learn, even if you're using PyTorch and TensorFlow for various utilities. There's also sort of custom tools that have been developed for high-energy physics. So there's one analysis framework called Root, and Root has its own basically version of scikit-learn called TMVA. For offline analysis, the existing tools I think work quite well. And then there's a lot of interesting work going right now for very fast inference, because a lot of our inference not only has to be very fast, so I mentioned 40 megahertz, but it also has to live in extreme conditions. So a lot of our detectors are either near in cryogenic temperatures, so they have to be able to work there, or in a radiation environment where you need to be able to operate in a case where the fluence of particles will damage the silicon, and so you need to be able to have robust inference. We had another question in. I've been interrupted, so I may have missed it, but are you using commonly available ML libraries like TensorFlow? Yes, we're using TensorFlow. I think I mentioned that. Okay, my question for contrastive learning was regarding anomaly detection in an unsupervised manner. You gave me a reference, so let me, maybe I will look at your reference and then happy to talk offline. I think my email should be available. I mentioned it on the first slide, and happy to share it to further discuss these topics. But thank you very much for the reference. And let me keep going. That was the same question. Okay. Was ML used for the discovery of the muon magnetic moment discrepancy? So the recent G-2 result. I'm not a member of the G-2 collaboration, the one that was recently, the measurement that was recently announced from Fermilab. I suspect that there was probably some machine learning deep in the analysis workflow, but I'm not familiar enough with the experiment to know for sure. Okay, so just to confirm, you are not using commercial systems like public cloud. I think there's a growing interest in using public cloud. I think there are some people who have started to think about how that could be used, but a lot of the analysis is done not with public cloud. So using basically our custom cloud as well as HPC centers. Your next question: are you implementing or planning to implement quantum machine learning on particle physics as well? So what's your opinion of quantum machine learning? There's a growing number of people who are interested in quantum machine learning. I think at the moment, we're not really limited by the kinds of things that quantum machine learning would help us solve. And in particular, for instance, for supervised learning, we have an immense amount of simulated data, and so we're not data limited. Often our data structures are very, very large and complex. So the near-term quantum computers, I think, are probably not appropriate. But there's a lot of interesting research going on in that direction to see if there are some places where quantum machine learning could be particularly helpful. My slide deck, this question on the slide deck, I'm very happy to make my slides available. They'll be on my website in the next day, so you can definitely check them out there. And I'd be happy to talk more to anyone who's interested in following up on the topics I mentioned. And I think that's the end of the questions. Are there any other questions?
Great. And
let me go to the first page. You can check out my website is my name.com.
Okay, that's easy to remember.
Yes.
Okay, great. Yeah. And later I'm also going to send some of those resources to the attendees, the links. I think that's it. Great. Thanks a lot for the presentations, and thanks everyone for joining us. I hope you learned something new. Please check our website for the up-and-coming events. So I hope to see you everyone in our next events.
Thank you very much. Take care.